let's go through the proof of L'Hopital's rule. So let's first look at the theorem again, or the rule again. We have that f and g are differentiable on the open interval from a to b, containing c, meaning c is in here. So it's differentiable except possibly at c itself. Okay, that's the assumption. If f of x over g of x has the indeterminate form of 0 over 0 or infinity over infinity at c, and if g prime of x is non-zero for all other values, meaning can't be c, then the limit as x approaches c or infinity of f of x over g of x is equal to the limit as x approaches c or infinity of f prime of x over g prime of x, provided the limit exists. So whatever this limit is, if it exists, has to equal this limit. So for our proof, we will show one case, the easier case. The other case is more difficult and shown in advanced calculus stuff, books. All right, so here's the start of the proof, and then we will continue from here. Let's hypothesis, right? Let's assume f and g are differentiable on AB for C and AB, except possibly at C. So differentiable everywhere except in the interval, except possibly at C. Okay. The next part is we want to suppose that f of x over g of x has the indeterminate form 0 over 0. This is the case we will show at x equals c, and that the limit exists. So we're going to assume as well that the limit of f prime of x over g prime of x as x approaches c equals L, meaning it exists. So we want to show that the limit of f of x over g of x as x approaches c also equals L. So we will define two functions like this. So here we go. We will define two functions, capital F of x equal to f of x, little f of x, if x does not equal c. And we're defining capital F of c to equal 0. And similarly, we're going to define g of x, capital G of x, to equal little g of x for same thing. If x does not equal c, and we will define that capital G of c is equal to 0. So f and g are both continuous at c. So f and g are both continuous at c. Since, to show continuity, you want to show that the limit, the limiting value equals the function value. So if you take the limit, so just showing that statement, since the limit of capital F of x as x approaches c is equal to the limit of f of x, little f of x, as x approaches c, which equals 0. Which is equal to capital F of c. So they are basically the same everywhere. And then this must equal 0, right? Because this is what it's assumed to be as a determinate form. Okay, and then, so that's for f. G is the same thing. And the limit of g of x as x approaches c is equal to the limit of little g of x as x approaches c, which is also equal to 0, right, because of this. Right, this has the indeterminate form at c. But that's equal to capital G of c, and so the limiting value equals the function value, which is 0. Okay, and I'll just conclude as well. So, and therefore continuous on the open interval from A to B. So the hypothesis is that f and g are continuous except possibly at C, but our capital F and capital G are continuous everywhere on AB. Okay, that's what that does. Okay, now we also have that, I'll write that down. So we also have that for x not equal to c, f prime of x is equal to capital F prime of x is equal to little f prime of x, and it just because of the way they're defined, and g prime, capital G prime of x is equal to little g prime of x. So that must be true because f and g are differentiable on AB for all values except possibly at C, and that these are defined to, these are equal. Okay, so then we have, so now we may apply Cauchy's formula. All right, so now we may apply Cauchy's formula to either interval. So to either interval C to X or to X to C, that there exists a W between C and X such that capital F of X minus F of C, this is the conclusion of the formula, capital G of X minus capital G of C is equal to capital F prime of W over G prime of W. But capital F prime and capital G prime at W are equal. So that's F equal to little f prime of W over G prime of W. So we're basically going around C, right? We're not going up to C, but we're saying we also have that when X is not equal to C, that these are true. Well, if you go back to our assumption, they're the same function except at C. Okay, so these, where'd it go? So these are because it's everything except C, right? So we're applying Cauchy's formula, excuse me, on these intervals. And then there's this, so the W is between C and X, so it's like the open interval between C and X that you can apply and get Cauchy's formula. So keep in mind, this is X, but this is W. So it's like the other value in between. All right, so we defined, now some more explanation, hopefully. We defined capital F of X and capital G of X so that capital F of X is equal to little f of X, capital G of X is equal to little g of X, and capital F of C is equal to G of C, which is equal to 0. So they're the same, but at C we define those to be 0. So then, or hence, we have that this basically cancels out. So you have, let's see, so because of this equal to 0, these guys are 0. All right, and so then f of, so f of x is capital F of x is little f of x, etc. And so we're going to replace that with f and g. Hence we have f of x over g of x is equal to f prime of w over g prime of w, meaning the existence of that w is there. Since w is always between c and x, you can take a limit. All right, so I'm going to move this over. Since w is always between c and x, it follows that the limit of f of x over g of x as x approaches c is equal to the limit of f prime of w over g prime of w as x approaches c. That's just because those are equal. But that means you get that this is equal to the limit of f prime of w over g prime of w as w approaches c, because it's always between it, so you can approach like that. But by assumption, this limit must equal L. Okay, so going back here, where'd it go? That's equal to L. So these must be equal as x approaches c. That's implying that w approaches c because c is always between, or w is always between c and x. So this limit equals L, which is what we wanted to prove. Okay, so that concludes the limit. I mean the proof concludes the limit. That's what we wanted to have. So it's constructing those functions to allow us to take the limits appropriately. So there's a lot of stuff in this one running around. So take some time looking through it. It's kind of like you're squeezing. So when you have this sort of thing going on, it's like you are, when you do this limit, this last one is one of the most important things to understand. You have, why are these equal? These are equal because of this. But x is approaching c, x is approaching c in that case. Now, because you have w always between c and x, you have this sort of thing going on. So here's c and here's x. W is always in here. So as x approaches c, let me erase that. As x is approaching c, it's as if, and then w basically starts to approach c as well. Okay, in which case, that's what we wanted to show, is that, like, what does it equal? Well, since these have to be equal, these have to be equal, which is approaching a fixed value, which is assumed back here, right here. Okay, that concludes L'Hopital's rule. And so you want to make sure you practice those examples we did in the first one and be able to apply L'Hopital's rule. Next is 7.6, inverse trig functions.